I'll begin. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray that you be with us this morning. Help us to understand the material we're covering and just to deepen our understanding of it. And we just thank you, Lord, for your grace and mercy for us each and every day, Lord. In your name I pray. Amen. All right. So hopefully, if everything goes, well, there's always snow. But modulo that. What hopefully will happen is Monday we'll have a retest, all right, like I announced. And then Tuesday we'll hopefully wrap up whatever we don't do today. And so if ideally, Tuesday we'll have time for homework questions you might still have about the homework which was supposed to be due originally when? 222? Yeah, it's on second order constant coefficient problem, least upper bound, sequences of real numbers, and sequential limits. So we should get through at least a little bit of the sequential limits section today. So we really should have a pretty decent shot at working most of the homework problems, which will be due Wednesday next week, given what we do today. So, all right. So I'm going to start with. Interesting. Any questions about anything before I just dive in again? All right, so this is one of the theorems from 11.1 I have not proved yet, but we should. Let me do it over here. Theorem 11.1.3, every non-empty set set of real numbers which is bounded below has a greatest lower bound. So the corresponding statement for non-empty sets of real numbers which were bounded above wasn't something we prove, it was something we took as an axiom in here, right? As I was mentioning, that axiom could be actually derived if you had a more finely, let's say, presented system of real numbers. If you cut things more deeply, you could derive that axiom from other things. But in some sense, that really is part of the definition of real numbers. All right. So here's the proof. Proof is actually really quite natural once you understand it. So let S, all right, be non-empty. Subset of R bounded below. Right? So what's that mean? That implies that there exists like n, right, in the reals such that what? N is less than or equal to x, right? For what? For all x where? What is it that's bounded below? The set S, right? So for all x in S, this set right here, right? Okay, so we don't know anything about, we don't have any theorems for this just yet, but what do we have? We have an axiom for sets which are bounded above. Can you think of how to take this set and construct some corresponding set which is bounded above? How about this? You might call it minus S. I'm going to call it T, though, just so it doesn't seem like it's just formal nonsense I'm doing. So let minus S equal T, but here's the real definition. T is the set minus X such that X is an S. So T is a set of minuses, additive inverses of elements of S. And you could argue, what can we argue then? Well, check it out. Note, if n is greater than or equal to x, that implies what? If you multiply an inequality by minus 1, what happens to it? Yeah, flips it, right? So that's minus n is greater than or equal to minus x, right? And that's still true, right? What does that say, though? What does that say? I mean, that says, hence what? T is bounded above by what? By minus n, right? Because minus n is bigger than every minus x, and those are the things which make up t. Okay, so t is a non-empty. By the way, t is non-empty because s is non-empty, right? That's clear. And so we have a non-empty set bounded above. So t is not equal to the empty set. I don't know if I talked about this last time, guys, but this notation here, it's a funny thing. This is the so-called empty set. It's a set which contains no elements. Dr. Skimbordas can talk about this for hours. So if you want to strike up a conversation about the empty set, say something incorrect about it to him when he's in a good mood, and he'll keep talking about it. It's one of his favorite topics. Anyway, t is bounded above by that. So by the least, by the what? By the therefore, by least upper bound axiom, what do we have? There exists what? Let's say m in the reals such that what? M is greater than or equal to what? Minus x, right? For each x and s. That's just saying that m is larger than everything in the set T. So then what? I mean, it's a little bit more than that, right? M is also equal to the what? The least upper bound of T, right? Our notation from last time. So then what? Well, what you can do then is to argue that if I do this, so look at this, if I do minus m, right, is less than or equal to what? X, right? For all x in S, right? So clearly, minus m is a lower bound, right? It's a lower bound for S. But we can also argue, in fact, that it's the greatest lower bound. How can we argue that m minus m is the greatest lower bound? So it is a lower bound. Suppose I need yet another letter. You guys pick it, whatever you want it to be. Something I haven't used already. W? Okay. Suppose W. I like it. Suppose W is another lower bound, right, of S. What's that mean? Hence, W is less than or equal to X, right? What? For all X and S. But what does that say, by the way? I mean, essentially the same argument we already went through. That implies that, what? Minus W is greater than or equal to minus X, right? For all X and S, right? But what does that mean? That means that minus w is a what? I mean, we already went through this argument. I'm going through it again, basically. That means minus w is an upper bound for t, right? Rather, minus w is upper bound for t. Okay, if it's an upper bound for t, how is it related to the least upper bound for t? By definition, right? By definition of least upper bound, we have what? We have, where is it? What was my least upper bound? My least upper bound was minus m, right? Minus m is less than or equal to minus w, right? It's the least upper bound. I'm not really interested in minus m and w, right? I'm interested in the relation of what? I guess I am. Oh man. Un momento. Uno momento. I've gone colorblind. Let's see here. Sorry. Teaspoon. Oh, I have failed to communicate what I'm trying to argue. I mean, I said we argue that minus m is the lower bound, right? But I really want to argue that minus m is not just a lower bound, it's in fact the what? I mean, I forgot to announce that here, didn't I? What should I say? Argue that this, so let me just put a little caret here, and no other lower bound is bigger, right? In other words, I want to argue that minus m is the greatest lower bound. How did I've gotten turned around here somehow. Maybe I tricked myself when I worked this out this morning. He uses contradiction in the book, and I thought, well, I've got a proof that doesn't use contradiction. Maybe I don't have a proof that doesn't use contradiction. See, because I need a statement about what I'm looking for, right? What do I want? I said, suppose w is another bound of s. What's my goal from this? Is to show what? What do I want to show? No other bound is bigger, right? So I want to show minus m is what? Less than or equal to w, right? Oh. Come on, guys. Don't let me get away with this. Look, I've gone all through all this trouble of talking about minus the set, right? Great. Worked our way all the way down here to showing that m is what? Greater than or equal to minus x, right? So then I multiply by minus. Oh, that's by least upper bound axiom. Fine. Curses. Where have I gone wrong? was to show minus m is less than or equal to w. The m is given to us by what? The least upper bound axiom, right? So I can multiply that by minus 1. That gives me minus m. Excuse me. So of course this is the least upper bound axiom applied to t, right? Minus m is less than or equal to w. So w less than or equal to x. That makes w a lower bound, right? This. Oh, wait a minute. So what's the least upper bound? Sorry. Duh. Okay. I think I fixed it. So we have what? Up to here is fine. I mean, I don't think I said anything wrong. I'm having trouble making the final concluding sentence here. So let w be less than or equal to x, right? Then this is true, since that's an upper bound for t, right? So note m is equal to the what? M is equal to the least upper bound of t, right? I was trying to put minus m in the place of this in my previous thinking. That was my mistake. So m is the least upper bound t. What's that mean? M, not minus m, is less than or equal to what? Minus w, right? And that implies what? Multiply by minus 1, right? We have minus m is greater than or equal to w, which is what? Oh, man. No way. Is that opposite of what I want? I'm trying to show that minus m, oh no, minus m is bigger than the other lower bound, right? So therefore, minus m is equal to the greatest lower bound of s. That is what I want. This was not our goal, right? That would not show that. That would show that w is a larger lower bound, right? This is backwards, yeah. If we want to show if we want to show that minus m is the greatest lower bound, right? That means I want to make w below it. All right. All right, so what is clear today is that if I'm ever asked to teach real analysis, I should refuse to do it at 8:15. Absolutely categorically refuse. Okay. Now it's fixed. Sorry for the delay. Obviously, I should have drank another cup of coffee or something. You know, you guys could jump in and tell me where I'm wrong. No? 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 All right. Where'd my notes go? I had a couple of pieces. Oh, they're there. I guess if I had just written what is on this page, we wouldn't have had this problem. That's why you should write notes and use them. All right. Now, finally, some examples. Another example I can give you, actually I'll do it over here. Another example I can give you of a sequence, which I haven't given you yet, it's an important example, would be this. Let's see here, a sub naught. And if you'll forgive me, I'm going to start this sequence at 0 and violate our definition just a little bit if you're okay with that. This sequence is going to start at 0. I mean, you can say, well, that's not really a sequence because you said sequences are functions of the natural numbers. That's kind of true, fine, but I want it to start at 0 for the sake of not introducing weirdness into the notation. a1 is 1, all right? And then a sub n is equal to n times a sub n minus 1. None of the above. But it's an example of a sequence. 11.2. It's not in the book. I mean, it's not in the book. I'm adding this example. It's an important example, though. Okay, so for n greater than or equal to 2, okay? So I'm suggesting we can recursively define this sequence like so. So what's A2? All right, 2. What's A3? What's A4? And so forth, all right? So, in fact, we have a special notation for this definition. We say that this a sub n is actually equal to what's called n factorial. And that's for n an element of the natural numbers union with 0. I need to throw, I just want to throw 0 in there just to settle it. I could start at 1, I suppose, but you should know 0 factorial is 1. It's important to this course. So, I mean, I guess my fundamental observation here is that, and this is useful for your homework problems, which is why I'm showing you this in part, is that we have this identity, right? Like n factorial is equal to n times n minus 1 factorial. So this is like the crucial identity, basic identity you know about factorial, which will help you solve homework problems, right? Okay, so there's another example of a recursively defined sequence that I haven't shown you yet. I need to define a few terms. So here I'm going to talk about increasing, decreasing, all that, all right? So we're given a real sequence, let's say a sub n. Then here's the definition. And what I'm going to do is he says certain terms in the book are standard. I just don't believe that's the case. So I'm going to change terminology a little bit. So you gotta watch with me here. Strictly increasing. We'll talk about what's strictly increasing. We'll talk about what's increasing. We'll talk about what's strictly decreasing. And decreasing. At least this is the terminology which is standard in all my other mathematical experience of late. This is the standard terminology, okay? And so what I'm going to do here is just make us a little table. So I'm going to put the defining relation in this thing. I'm going to put a derived consequence in this column. And then over here, I'm going to tell you Salas and Hilly's, or Salas and Hill's. And what's the third author? We never say his name. Oh, well. There's a third author, Etjen or something. These guys, what their terms are. All right, so what they say strictly is strictly increasing. They say strictly increasing. They actually call it just increasing, which is unfortunate. They say increasing is non-decreasing. They say strictly decreasing is just decreasing. And they say decreasing is non-increasing. And I understand his choice of terms. I just don't want to teach you them because they're not standard. And in other courses, when you talk to other professors, unless they've been recently teaching out of this book, they will assume that you're using the meaning on the left-hand side, not the right-hand side. So I want to adhere to standard terminology. And unfortunately, I just don't think the book is correct. Now, strictly increasing means that the terms, all right, are getting larger. So like a sub n is less than a sub n plus 1. Increasing allows the possibility of constant. So it's just less than or equal to. A sub n is less than or equal to a sub n plus 1. Strictly decreasing means the terms are getting smaller. So like, as I'm writing it now. And then let's see here. And then decreasing means they're getting smaller, but they could be equal. Right. So under this definition, all right, and again, whenever I say these terms, I'm going to use my definition. I'm trying to warn you, it's not the book's definition. I'm sorry about that, but like I said, it's for the greater good. So in our definition, which I've given on the left-hand side here, a constant sequence, for example, would be both increasing and decreasing. So a sequence which is everywhere increasing and everywhere decreasing would just be a constant sequence in my definition, right? Now, I totally agree. I mean, we both agree on what's monotonic. A monotonic sequence, for me, monotonic means either increasing or decreasing, right? That's what I say. Monotonic is either increasing or decreasing. Notice that strictly increasing implies increasing. Notice that strictly decreasing implies decreasing. So the strictly increasing or strictly decreasing are special cases of increasing and decreasing, respectively. So I can just say a monotonic sequence is one which is either increasing or decreasing. What Salas and Hilly says is a monotonic sequence is any of these four cases, which is a little bit out of character in some sense because those cases are not distinct. They're overlapping, and he doesn't seem to be saying much. Well, anyway, whatever. Who cares? Now, here's the cool thing. The way to actually study this in problems is to look at this, and you can see this if you read the text. Like what he does is he doesn't try to attack these conditions directly. Those are kind of like harder to wrap your mind around. What's easy to wrap your mind around in terms of inequalities is the number 1. So like if we look at an plus 1, right, over an, we're going to look at that in each one of these cases. An plus 1 over an plus 1 over an plus 1 over an. Then you can compare these to the number 1, either greater than or less than the number 1, each one. So you guys tell me. Like if it's strictly increasing, that means this quotient is what? Greater than 1, greater than or equal to 1, less than 1, or less than or equal to 1. So if I want to check a specific example and see whether or not it's, strictly increasing, or I guess I should probably punish the later section by butchering this proof too. I actually didn't really butcher it. I just put a giant awkward pause at the end. I'm sorry about that. So some examples. We can show, for example, that a sub n defined by so I'm trying to follow the book more or less, but I'm trying to explain what the book is doing. So a sub n over n plus 1. Okay, so we can show that this is increasing. I mean, you can plug in some numbers. Just plug in a few numbers, right? Plug in, I mean, what does this give us? This goes to what? This is 1/2, right? 2/3, 3/4, 4/5, so forth and so on, right? By the way, there's something I should clarify. I said that you could identify this list of numbers with the sequence, and that's true. But we could be more specific. If we're saying that the sequence is a function, that list of numbers is in fact a specific thing. This is actually the range of the sequence. So I don't have to be esoteric about it and say we can identify it. No, I can just tell you explicitly that's the range of the sequence. And that's important because the range of the sequence is a set. And since it's a set of real numbers, we can apply the theorems we have about non-empty real numbers, like the least upper bound axiom and other things. So the range of a sequence is a set, and that's useful because we can apply 11.1 to that. That's just a comment. All right. Getting back to the example. You can see, right, you can look at this, and you can kind of see what's going to happen, right? You've got what? 1/2 is less than or equal to a sub n is what? Less than 1, right? So you can see that if I call this, you got what, the greatest lower bound of the range of an makes sense. If we're talking about the greatest lower bound of a set, well that's a half, right? And what is it also equal to? You could say. Well, I mean, it's 1, right? I would say that since it's in the set, it's actually the minimum, right? In terms of the terminology I introduced yesterday. All right. Just going over that because the book goes over it. Let's get back to the question of increasing and decreasing. Is this sequence increasing, decreasing? Is it strictly increasing? Is it strictly decreasing? Which flavor? Yeah, looks like it's strictly increasing. So what we got to do to judge that, the merits of that claim, is we just look at, let's see here, the quotient of an plus 1 over an. We're trying to show it's greater than 1. All right, so what is that? Here, that's n plus 1 divided by n plus 2, right? That's a sub n plus 1, right? And I'm dividing by n over n plus 1. And then I can just do algebra. Like I've got myself a n plus 1 squared upstairs, and downstairs I've got an n times n plus 2. When I first saw this example, I'm like, how on earth am I going to show that that's less than 1? That's kind of scary, but not really. If you just multiply things out, n squared plus 2n plus 1 divided by n squared plus 2n is what we're facing, right? And at this point, the textbook just says, oh, okay, well, clearly that is greater than 1. So therefore, the sequence is, and let me skip the brackets here. Let's just say a sub n is strictly, he wouldn't say that, I would say that, strictly increasing. And by the way, we can abbreviate increasing to inc if that's okay with you guys. All right. Well, I mean, truth be told, even if it's not okay with you guys, I'm still going to do it. I admit it. I'm callous in this sense. Look, can you guys understand that inequality? Does it make sense to you? Why? I saw nodding. It just feels right? Or like, is there like a specific reason that this makes sense?
It has to be greater than 1 because the plus 1 is greater.
So I think I'm going to put some words in your mouth here. You're saying this is a positive number alpha greater than 0, right? So the pattern we're looking at here is alpha plus 1 over alpha. And clearly, if you have a positive number and you add 1, and you divide by the same positive number, that must be greater than 1, right? Now, you're like, some of you are still unconvinced. Well, that's not basic. Like, that's not something I learned as something I should remember forever and ever. Well, fine. For those people, I would point out that this is the same as alpha plus 1 greater than alpha. Because why? To quote my little brother, circa 1980, 1989 or so. Cos by. Cos by. No, cos by is not an argument. It's a saying of my little brother. This being greater than 0, I can multiply, and I don't swap the inequality, right? Don't change the order. So this is interchangeable given this precondition. Then what? This is the same as what? Subtract alpha from both sides, 1 greater than 0. At this point, we all agree. So I've now shown you that that common sense inequality being greater than 1 is equivalent to 1 greater than 0. Hence, it's true. Okay. Let's look at another example. Example 2. We have a sub n equal to 3 to the n over n factorial. And we're going to say n is greater than or equal to 3 for my convenience. All right, so what we're going to do is we're going to look at a sub n plus 1 over a sub n, and we're going to study that. And we're going to see if we can't just figure out from looking at this quotient whether it's increasing or decreasing. Again, there's really nothing stopping you guys from plugging in some values and deciding before the fact whether we should be searching for less than 1 or greater than 1, right? Do you see intuitively what it must be? I mean, n factorial, right, is like n times n minus 1 times n minus 2, right? So it's products of numbers 1 through n, right? And that just keeps getting bigger and bigger and bigger and bigger, right? On the other hand, 3 to the n is just 3 times 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 3. Eventually, the n factorial is always multiplying numbers which are bigger, right? So the n factorial should win. I mean, this is as much as is true about a cage match between functions. Like, given a cage match between a polynomial and an exponential, I always bet on the exponential. But if you see a factorial enter the stage, game over. So, and then there's like n to the n, and I can't remember where n to the n fits into things, but n to the n is also a legit competitor. You got to watch out for that one. Don't worry, we will study all these things. We will put them in the octagon or whatever it is. I don't really watch that stuff. I don't know. I wonder what the percentage of Trump supporters is in the Ring of Honor viewership. I wonder. Just wonder. Sorry, I digress. Let's see here. I'm very torn. I mean, on the one hand, I like to make fun of the Pope. But on the other hand, the Pope. We still have a Pope at this day and age. It's kind of funny. Let's see here. 3 times 3 to the n times what? N factorial divided by 3 to the n times n plus 1 factorial. Well, but what's n plus 1 factorial? I can write it as n plus 1. Tell you what, I'll put it in, before I do anything funny here, let me just put it in the top and the bottom. Then I'll use my algebra identities for the next step. How about that? All right. I just made things into a single fraction. Next step, apply laws of exponents, which gives me 3 to the n times 3, right, times n factorial. Definition of the n factorial, which I just talked to you about over here, it's really n plus 1 times n factorial. So these n factorials cancel, and the 3 to the n's cancel, like so, and then we've got 3 over n plus 1. But let me write that down. So we have a sub n plus 1 over a sub n is equal to 3 over n plus 1. Now I also have what? N is greater than or equal to 3, right? Excuse me. So what happens if I replace n with 3? 3 is a number what? Smaller than n, right? If I replace the n in the denominator with a 3, I have made that fraction what? My question to you is this less than or equal to, or is it greater than or equal to? You choose the adventure here, 3 over 3 plus 1. See what I did there? I'm just replacing this n with this 3 in view of that. Which should I circle? Greater than or equal to, or less than or equal to? All right. Hey, that's good, because this is what? 3/4, which is obviously less than 1. So we have that an plus 1, right, over an is strictly less than 1, right? Therefore, the sequence is strictly decreasing. Yep.
You wrote the
Uh-oh.
factorial identity in blue. If you look down where your observation is, you seem to switch the n and then n minus 1.
Well, I can write this as n plus 1 factorial equals to n plus 1 times n factorial. Or I can write n plus 13. Factorial is n plus 13 times n plus 12 times times n plus 1 times, I mean, there's all kinds of flavor choices here with factorial identities. You can go on. We're just scratching the surface today, really. Okay, so those are some examples of increasing, and there's 2 more examples in the book which I would encourage you to look at. But I want to spend the remaining time today talking about a little theorem, which is the following. It says that every convergent sequence is bounded. You know what? I don't really have proper time to do that theorem decently today. So what I'm going to do is I'm just going to do the other 2 examples of increasing and decreasing sequences. Sorry to be boring. I was hoping to cover every convergent sequence is bounded, which is a simple extension of the theorem we proved yesterday. And I also wanted to state for you the theorem 11.3.6, which is that a bounded, basically it just simply says this: a bounded monotonic sequence converges either to its greatest lower bound or its least upper bound as appropriate, which is, that's kind of the punchline here of this whole discussion. We're just not going to get to it today, but it's okay. These will be helpful to you, these examples, if we work them. So let me do it. Example 3. If we have c greater than 1, and if I have a sub n equals to c to the n, all right, then we can look at a sub n plus 1, right, over a sub n. What do we get? Which is what? C to the n times c over c to the n. So that's just what? C. Which is by assumption what? Greater than 1. Therefore, a sub n is a strictly what? Increasing sequence, right? Another example. A sub n is equal to n over e to the n. So yeah, we're currently in, I guess these examples are in 11.2. So I will, hopefully, when we get back on track here Thursday, Tuesday, I hope it's not Thursday. God, creep. So hopefully we'll come back Tuesday. I will present to you the other main tools for analyzing limits of sequences, all right? So I haven't talked about the limit of a sequence today yet, really. But that's what that theorem I was just mentioning does for us. It connects the greatest lower bound and the least upper bound for sequences whose range is bounded either above or below as appropriate to the convergence of a limit. So these things get connected in that sense. Anyway, back to this example. I guess we could try to attack this directly. I don't know, the book does not try to attack it directly. Let's see what happens if we try to attack it directly using the same method we've used for the last 3 examples. What will happen? Just look at an plus 1 over an. What do you get? Which is, I can rewrite in a better way. This is n plus 1 times e to the n divided by n times e to the n plus 1, right? Now, of course, we can simplify that a little bit. That's n plus 1 times e to the n over what? N times e to the n, right? Using lots of exponents. Oh, hey. I think the book is smarter than it needs to be here. I think we can do this without calculus. Sorry, obligatory sound effect. N plus 1 over ni. So what's the deal with that fraction? How is it relating to 1? Plug in some n, right? Let's see what happens. Just do some trial and error to start with, if nothing else. If I plug in 1, right, I get 2 over 2 over e. E is 2.717. It's less than 1. Plug in n equals to 2. 3 over, what's that? 3 over 2e. So it seems like it's going to be, I think it's going to be less than 1, right? So the question is, this is less than 1, can we prove that? So let's see here, n plus 1, we just kind of set it aside here. N plus 1 over ne less than 1, right, is equivalent to what? It's equivalent to n plus 1 less than ne, right? Which is interchangeable with what? N minus ne less than minus 1, right? Which is the same as n times 1 minus e is less than minus 1, which is equivalent to n is less than, well, you got to be careful. If I divide by 1 minus e, what can you say about that quantity? Yeah, that's a negative number. So if I divide by that, the inequality flips, right? So this is n greater than minus 1 over 1 minus e, but hey, that's equal to 1 over e minus 1, which is what? I mean, that's essentially 1 over what? 1.7-ish? So this is equivalent to n being greater than 1 over e minus 1. And I think that, let's see, that's what? Isn't that true? I think that's true for n equals to 1, right? I mean, you could say this. N is greater than or equal to 1, which is greater than 1 over e minus 1. So, in fact, given these, Now, your book uses a calculus argument, which I'm not sure is easier. Well, anyway, I shut up. I think my time is up, right? So, have a good weekend, you guys. I really do hope that you earn more points on Monday.
Me too.
Right? So, yeah, you can cut it off.